and welcome to week 2 of Advanced Algorithms. In this week, we will be talking about a combinatorial object called a matroid. That will be the main focus throughout the week. Last week, we talked about greedy algorithms quite a bit. We saw several individual examples of greedy strategies at play. And this week, we will be looking at an abstraction that allows us to generalize the sort of principles at play that make greedy algorithms work. So we will be looking at a fairly general theorem establishing the correctness of greedy strategies in a wide range of circumstances. Essentially, what we will show is if your optimization problem has what we will call a matroid structure, then a greedy approach to that problem will actually work. And this turns out to be a very powerful framework because now, when you're faced with a problem for which you have a greedy strategy, instead of trying to prove that the strategy is correct by hand, which is what we did for most of last week, what you can instead do is try and establish that your problem has this matroid structure, and then basically the proof gets outsourced to the theorem that we will be seeing this week. So that's going to be quite nice. In fact, if you have seen the minimum spanning tree problem before, it turns out that the correctness for the greedy approach to minimum spanning tree can be thought of as a special case of the theorem that we will see this week. So that's one interesting application already. And we will look at another problem called scheduling with deadlines, which will be a concrete algorithmic question. And while we could have approached it the same way that we did last week, that is to say, we come up with a greedy solution and try to either brainstorm counter examples and play the adversary and try to figure out if it doesn't work, or if we are really convinced that it works, then we try to come up with a proof. So we could go through that whole process. But since we would have just proved something interesting about matroids, what we will do instead is show that the problem has the matroid structure, and we will not give an explicit proof that greedy works, but instead we will just rely on the correctness of the matroid based algorithm, and that will be that. So we will see one concrete application, and we'll also see several examples of matroids. So I've said a lot without actually telling you what matroids are, and in fact I will not be telling you what matroids are for some more time. What I want to do first is set up a generic optimization problem for you to consider, and we will try to just come up with a greedy approach for this problem. And we will see that, well, we are being too ambitious in this context, and the greedy algorithm, this is a bit of a spoiler alert, but it will turn out that the greedy algorithm will actually not work. And then we will try to think about what constraints or restrictions can we impose on this very general setting so that hopefully our greedy algorithm actually works. So it's going to be some serious reverse engineering towards the definition of a matroid, so that hopefully the definition will strike you as being somewhat well motivated, as opposed to being something that was pulled out of a hat out of the blue. I should say that matroids are a very fundamental combinatorial construct. They go back all the way to the 1930s or so, when the mathematician Whitney introduced them, and they show up in various contexts, but our focus will be on the way they show up in the context of greedy algorithms. Okay, so with that said, let's get started. What is this generic optimization problem that I want to discuss? Well, what we have is a universe, which I will denote by U. You can think of this as a discrete collection of elements, and we will denote the elements by E1 through En. So it's a discrete finite collection of elements, there are n of them. And what we will also have is a weight function that associates with every element in the universe non-negative weight. So you could think of these as non-negative integer weights, real weights. I will go with rational weights here. All right, so what else do we have? What we also have is a family of subsets over the universe. So we have F which consists of the sets S1 through Sm. So this is a collection of M sets. Each Si is a subset of U, and the weight function naturally extends to this collection of sets. So I could also talk about the weight of a set S. So if S is some subset of the universe, its weight is simply the sum of the weights of all the individual elements that are contained in that set. So that would be how you extend the weight function from the universe over to the family. And so that's the input. Now, what's the question that we want to address here? I said that we will be talking about an optimization problem. So the optimization that we want to do here is to find a set S in F that has the largest weight. So find me the max weight set in F. So that's the question we want to think about. You could also define a minimization problem, and we will come back to that later. But for now, just to keep things simple, I want to focus on the maximization variant because it's just a little bit more natural to talk about. So you might be wondering at this point, what's the big deal about this? What we could do is just go look at the sets, calculate their weights, sort them in increasing order of weight, and then just pull up the sets that have the maximum weight, and any of them would qualify as a valid solution to this problem. And you would be absolutely right. I think that's a fairly natural approach to this problem at this point based on what I've told you. But I should probably confess now that I did a little bit of false advertising by calling this the input, because it makes it sound like I'm giving you both the universe and the family on a platter, which is actually not the case in most applications of interest. In most applications of interest, what you're given explicitly is the universe, and the family is defined implicitly, meaning it's defined using some property. So just to make this a little bit easier to understand, let me give you an example. So the universe could, for example, correspond to the vertex set of a graph G, right? So all the elements in the universe are the vertices of a graph, and now your family could consist of, for instance, paths in G. So each set, to qualify for being in the family, should be a collection of vertices which can be ordered in such a way that they induce a path in the graph, right? It could also be independent sets in G, for instance, right? So a subset of vertices belongs to F if, when you look at the graph induced by that subset, there are no edges in them. That would be an independent set. So essentially your family is not given to you explicitly because, as you can imagine, the number of independent sets in a graph, the number of paths in a graph could be exponential in the number of vertices. The number of these sets could be exponential in the size of the universe. So it would be really expensive to list them out, and if that's what we did, then the problem would not be so interesting anymore, because then the input itself is so large that in time that is polynomial in the input you can do a lot of things. So that is not really going to be our setting. A setting is going to be that the family is given to you implicitly. What that means is, if you give me a subset of the universe, I can quickly tell you if that subset belongs to the family or not, right? So that is what is sometimes called an oracle, or you're said to be given oracle access to the family, which means that somebody gives you a set or you give me a set and I will validate for you if it belongs to the family or not. So with the examples that we have seen, that is something that you can do easily for independent set, for instance, right? Because given a collection of vertices, I can just look at them pairwise and it's going to be easy for me to confirm for you if that's an independent set or not. So that's a situation where the assumption of oracle access is actually very reasonable because you can do it yourself. Now, when it comes to paths, on the other hand, it's a little bit tricky, because if I give you a collection of vertices, it's not obvious whether there is an ordering of them that induces a path. That's something that is not easy to tell just by, looking at the vertices. You will actually have to experiment with all possible orderings. That would be one sort of a brute force approach to figure out if the set belongs to the family or not. Or you could use your favorite algorithm for checking if a collection of vertices has a path or not. That would be essentially some sort of a Hamiltonian path algorithm, and you would have to run that. So for that example, the oracle access assumption is a serious one, because you are just assuming that you have a black box which can tell you if a collection of vertices induces a path or not. So those are a couple of examples of implicit representations. The overall point being that the family is not given to you on a platter. You don't have an explicit list of all the sets in the family. You only have an indirect way of knowing if a set belongs to a family or not. So you can come up with a set and feed it to the black box and figure out if the set belongs to the family or not. And that is all that you have in terms of accessing the family. Given this, it becomes a lot more interesting to try and figure out which set has the maximum weight, because now it's almost as if you are moving around in the dark a little bit. You don't see the sets explicitly, but you can sort of try to build them out. You do have these universe elements which you can think of as Lego blocks, and you can try to figure out, how to combine them in ways that hopefully build up a set which is the set that you are actually looking for. So let's think of a natural greedy approach to this problem. Remember, we are given a universe, we know the weights of the individual elements, and we have a black box which will take a set as input and tell you whether it belongs to the family or not. Okay, so it'll say yes if S is an F, and it'll say no if S is not an F, and this is your oracle. So this is what you have as input. You have the universe, the weight function, and then you have this oracle, right? And the goal is to find a set that has the largest weight among all the sets in F. And one natural approach to this, if we are thinking greedily at least, would be to try and add elements which are as heavy as possible, right? So let me put this on the side here. Okay, so let's say that we sort the elements of U in decreasing order of weight. Why decreasing? Because this way the heaviest elements will show up first, right? And then what we are going to do is actually include these elements in our solution. So we also initialize a solution set, which I'm going to call X, to the empty set. And then we are going to say while so this is just an informal way of saying keep going until you still have elements remaining in this sorted order, right? I could have also simply said go from 1 to n, but that would also work. What do we want to do here? We want to check if I hope this makes sense. What we are saying is that look at the current element. If it's possible for me to include this element in my set, then let's include it, right? Otherwise, we discard the element and move on to the next one, right? And so either way, we should have some way of saying move on to the next element on the list. So let me actually walk you through an example of this algorithm running through a bunch of elements with some given weights so that we have some intuition for the mechanics of what is going on. Before that, I should note that it is in this step that we are invoking the oracle to check if we can actually incorporate the current element or not, right? So let's actually work through an example quickly. So let's say our universe consists of the elements W, X, Y, and Z. Let's say that the weight function assigns a weight of 50 to W, 30 to X, 42 to Y, and 10 for Z. So what's the family? Well, normally we would only have the oracle access, but since we are doing an example, let me write out a family for you explicitly. So let's say we have the singleton set W, and then we have X and Y, and then we have Y and Z, and we also have the singleton set Z. Okay, so that's the family, and if you like we can also calculate the weights of each of the sets in the family as well. So this one here is just 50. X and Y put together would be 72. Y and Z put together would be 52, and Z alone is going to be 10. So those are the weights of the sets in the family, right? Now let's think about what the greedy algorithm would do. The greedy algorithm would line up these elements in decreasing order of weights. So W comes first, followed by Y, followed by X, followed by Z. And we have initialized a solution set, which is capital X, to being the empty set. And now what we are going to do is run through this list from beginning to end and include as many elements as we can. So our first encounter is with the element W, and the empty set union W is just the set W, and the set W does belong to the family. So this if condition here will actually trigger to true, and we will include W in our solution. So X will get updated here to the singleton set W, and now we move on in the list because we have processed W. So now we go to Y, and now we try to add Y to X. So the set we will have is WY. We feed that to the oracle, and the oracle tells us no luck. WY does not belong to the family F, so you cannot include it in your solution. So we don't change X here, but we move on in the list, and the next element we go to is X, and we ask the oracle, is WX in the family F? And once again, that's a negative. WX is not in the family F. So once again, we don't change X and we move on. And as you can probably predict, the same thing happens with Z as well. So WZ is not in the family, so we have to eliminate Z from our consideration, and our output is just going to be the singleton set W from the family. So our output has a value of 50, whereas you can probably see here already that the optimal solution was XY, and the greedy procedure missed it. And the reason we missed it is because we prematurely held on to the element W, and that kind of blocked out access to XY, right? So that was one issue that we ran into, at least with this run. The good thing about this algorithm is that it always produces something that's in the family. So to that extent, you will get a valid answer. But you can experiment with examples yourself to see that the value of the output can be very different in terms of being much smaller than the value of the optimum, right? So in general, if we just try to build up a set in a greedy fashion, that's not going to work. But if you think about what Kruskal's algorithm does, if you're familiar with Kruskal's for minimum spanning tree, there, what's the universe? The universe is the set of all edges in your graph, right? And what is the family? The family is basically all subsets of edges that induce acyclic subgraphs. So essentially, all forest subgraphs of the graph G would constitute your family. And if you want to build a max weight spanning tree, for instance, this is exactly what Kruskal's algorithm does, right? It sorts the edges in decreasing order of weight, and it tries to pick the heaviest edge in each iteration, as long as that edge does not create a cycle, right? So that's what Kruskal's algorithm does, and it turns out that it works. We can actually prove that that algorithm outputs an optimal max weight spanning tree. So why does it work? It's got something to do with the fact that the collection of forests in a graph is not just some completely arbitrary family. It has some additional structure. And the question is, what is that additional structure that this collection has? If we can abstract that out, then we are one step closer to trying to understand for what kinds of families, for this generic optimization problem, for what kind of families does the greedy algorithm produce the right answer? That's what we want to address. Let's just briefly talk about how we would go about proving that the greedy algorithm works if we had to. Of course, we know that it doesn't work, so we know upfront that our proof is doomed, it's not going to work. But typically, if you had to show that greedy is correct, what's a standard exchange argument? What does it look like? So we're going to say, let's look at the output of greedy, and let us look at the optimal solution as well, right? So let me organize the output of the greedy solution by arranging it in some fashion. I should probably not use EIs because I've already used them to represent the elements of the universe. So let me just call this output F1, F2 up to Fk, where each of the Fi's corresponds to some element of the universe, and they're organized in such a way that the weights are in increasing order. And let's take the optimal algorithm, and let's say that those elements are G1, G2, and let's say some GL. Of course, we have no reason to believe that L is the same as K, so we could have fewer or more elements in the optimum solution, but let's also organize these in terms of non-increasing weight, so the heaviest elements come up the earliest. So if greedy falls short of being optimal, that means that there must be some point where its solution differs from the optimal. It could happen at the very beginning, right? Or it could happen somewhere in between. So just for the sake of conversation, let's say that F1 to Fp and G1 to Gp happen to be the same elements, or even if not the same elements, let's say that up to this point greedy is doing as well as opt, right? So let's say that for each of these choices, the element that greedy chose in that iteration was at least as heavy as the element chosen by the optimum solution. And there must be some point where this flips, right? Because if this is the scene till the very end, again, assuming for now that both greedy and opt have the same number of elements, even if not, actually, what I want to say here is that you must be in a situation. So for instance, it's possible that greedy runs out of elements here, and the optimum solution has picked up more. or it could be that they actually have the same length, but at this point greedy has picked something that is less heavy than the corresponding optimum choice. My main point is that this sort of a thing must happen at some point, because if not, then greedy already outperforms opt, or is at least as good as opt, and then we would not be having this conversation. So we are trying to understand, why did greedy fall short of opt when we are trying to prove by contradiction, right? So the only thing that I should note is that this may be a non-existent element. It's possible that greedy did not pick up as many elements as opt did, but the point is that you cannot have just this sort of a scenario till the very end, because what we have assumed for the sake of contradiction is that greedy falls short of opt. Now, typically in an exchange argument, this is where we drill down deeper and we ask ourselves, why did greedy make this choice? Why didn't greedy pick up this element, which was actually the heavier element compared to the choice that it made, right? That's what we want to ask ourselves. And if you look at the example, the counter example that we had, where greedy's first choice was W and the choices for opt were X and Y, right? So if you look at the first choice, W was heavier than X, but then we got stuck, we ran out of elements. And the reason we did not make the choice of Y was because it was not compatible with what we had picked earlier, right? So we couldn't have picked Y simply because when we tried to merge Y with W, we got something that was not in the family, and that was the problem. So if the structure of the family can somehow reassure us that we will not get stuck in this fashion, that if you have two sets of this sort, there's always something that you can pull in from the bigger set, which is the set here, and include it in the smaller set, which is the set here, then there is some hope that we can make this proof work, right? So if somehow the structure of the family was such that it promised us that you're never going to get stuck like this, you'll always be able to pull something in to the set that you're building, then you will hopefully be able to actually complete this argument. As of now, the argument is getting stuck because of this compatibility issue. So it turns out that the definition of a matroid actually allows us to drag GP plus 1 or an appropriate element from the optimal solution into the greedy solution, and it's a combinatorial guarantee which will help us not get stuck at this stage of the proof. That's what is going to happen. So when you see the Matroid definition, you will probably be able to appreciate why it's going to be so useful in the context of greedy algorithms. So hopefully that's enough of a teaser to have you feel motivated about defining matroids. The main takeaway is that we have this generic optimization problem which can capture many specific problems, and so if we had an algorithm that could correctly solve this optimization problem, then that would be really nice, because when we are working with a specific problem, we can just map it to this setup and check if our family satisfies the structural properties that we need for the greedy algorithm to go through. So that has been our goal throughout this discussion, and now we are trying to reverse engineer what properties can we impose on the family so that the proof of the correctness of the greedy algorithm goes through, and that's what we're going to do next. So in the next part of this this series of modules, what we're going to do is we're going to define what a matroid looks like, and we're going to come back to this proof, and we'll see that if the family happens to be a matroid over the universe U, then the proof that we were attempting will actually go through. Okay, so in the next video we're going to define a matroid, and we are going to look at some examples, and then after that we will come back and establish that the greedy algorithm actually works. And once we are done with that, we will look at the problem of scheduling with deadlines as a concrete example of how we can apply all of this machinery on a specific problem. So that's what's coming up. I will see you in the next video. Thanks for joining me as always.